Welcome everyone, let's dive right into this explainer. Today we're exploring the fascinating toolkit that public health experts use to track diseases and actually prove if treatments work. We're talking about the science of epidemiology, which is fundamentally about understanding the distribution, the determinants, and the control of diseases in populations. But more specifically, we're going to look at exactly how these researchers do their detective work.
I mean, have you ever scrolled past a flashy medical headline and wondered, how did researchers actually arrive at that conclusion? How do they know for sure that smoking increases the risk of cataracts, or that too much screen time causes dry eyes? Well, it's not just guesswork. It all comes down to the very specific study design they choose to investigate the problem.
So here is our agenda for today. First, we'll look at the toolkit. Then, descriptive observational studies, followed by analytical observational studies. Fourth, group-level ecological studies. Fifth, experimental study designs. And finally, choosing the right tool.
Starting with Section 1, the Epidemiologist's Toolkit, Observational versus Experimental.
So the crucial point here is that absolutely every tool in a researcher's kit falls into one of two main buckets. Basically, are we just watching as detectives, or are we actively intervening, like a controlled sting operation? In observational studies, researchers literally just let nature take its course. They observe exposures and disease occurrences without stepping in to change a thing. But in experimental studies, the researcher actively introduces a treatment or an intervention to determine its effectiveness.
Moving right along to Section 2, Descriptive Observational Studies, explaining the who, where, and when.
Let's start at the absolute ground floor of the evidence ladder. It all begins with a case report, which is literally just observing one single highly unusual patient. For example, imagine a doctor writes a detailed report about a patient who suddenly developed acute angle closure glaucoma, and it was triggered by taking a completely standard antidepressant medication. Now, it's just one person, right? There are no control groups, and it has pretty weak, broad applicability. But why does this matter? Because noting that one unique, novel presentation is often the very first clue that a brand new problem even exists.
Now, if we start seeing that exact same thing happening to multiple people, it levels up into a case series. A really great example from our sources is when researchers noticed a sudden progression of an eye condition called keratoconus in a group of patients right after the COVID-19 lockdowns. By looking at this whole series of patients, they hypothesized it was actually due to increased screen time and eye rubbing while everyone was stuck at home. So a case series builds our initial knowledge and helps generate hypotheses that we can go and test later.
Then, if we want to see how widespread an issue is at one specific moment, we take what's basically a snapshot using a descriptive cross-sectional study. Think of this as taking a giant photograph of a whole population at a single point in time. If we want to know the prevalence of dry eye disease in students, we just survey them. It's easy, it's super cost-effective, and it tells us exactly how common a condition is right now, even if, self-reported surveys can sometimes be a little bit inaccurate.
Next up is Section 3, Analytical Observational Studies, explaining the why. Okay, now we are stepping up the ladder. Analytical observational studies shift our focus from just describing what is happening to analyzing why groups have certain characteristics. And the key difference here? Comparisons. Analytical studies absolutely require comparing different groups to figure out if certain factors are causing a disease or protecting against it.
First up in our analytical toolkit is the cohort study, and this one is forward-looking. We start with a healthy group of people, folks who are completely free of the outcome we're studying at baseline. Then we track them over time to see who actually develops the disease. So imagine conducting a longitudinal study tracking school children over 5 years to see who develops myopia or nearsightedness. Because we're following them over time, this design is fantastic for proving a temporal sequence, meaning we can prove the exposure actually happened before the disease. But as you can probably guess, watching people for 5 whole years is expensive, time-consuming, and people tend to drop out of the study.
To really lock this concept in, let's contrast that forward-looking cohort study with a case control study, which works completely backwards. This is a vital distinction in epidemiology. A cohort study looks to the future. A case control study looks to the past.
In a case control study, we actually start with people who already have a disease. We call these our cases, and we compare them to individuals without the disease, our controls. Then we play detective by looking backwards at their past histories. Say we want to know what causes keratoconus. We find patients who already have it, we find similar people who don't, and we compare their past habits, like eye rubbing or allergies. Because we start with the disease already present, this is an incredibly fast and inexpensive way to study super rare diseases.
We also have an analytical version of the cross-sectional study. Just like the descriptive version, it's a snapshot,
But here, we measure the exposure and the outcome at the exact same time to find an association, like measuring hours of screen use and dry eye symptoms among office workers simultaneously. But here is the big limitation you need to take away from this. Because we measure them at the very same time, we cannot prove causality. It's the classic chicken or egg problem. We know the two things are linked, but we just can't definitively prove which one came first.
All right, Section 4, Group-Level Ecological Studies, focusing on group-level data.
Here, we are zooming out completely from individual people to look at entire populations. An ecological study uses group-level data, comparing massive trends. Instead of looking at individual patients, the units of observation are entire neighborhoods, provinces, or even whole countries. For instance, looking at regional sunlight and UV exposure levels across different countries and comparing that to their national rates of eye diseases like pterygium. It's an awesome way to generate hypotheses using data that already exists. But you have to watch out for what's called the ecological fallacy. That's the trap of assuming an association found at a massive group level automatically applies to a single individual.
Moving on to Section 5, Experimental Study Designs, using active interventions.
Now we have reached the very top of our ladder, where the researcher stops just watching and actually starts doing. Randomized controlled trials, or RCTs, are the absolute gold standard of epidemiology. They follow a super strict multi-step process. First, participants are randomly assigned to either receive the intervention or join a control group. This randomization is absolutely crucial because it massively reduces selection bias. Then, the treatment is introduced, like giving one group atropine eye drops for myopia control while the control group gets a placebo. Finally, we compare the outcomes. By controlling the environment so tightly, we get highly reproducible, trustworthy results.
But sometimes we use a really clever variation called a randomized crossover trial. Instead of having a totally separate control group, a participant tests one treatment, takes a break, what we call a washout period, to ensure there are no carryover effects, and then they test the other treatment. They literally serve as their own control. This is brilliant for things like comparing two different types of contact lenses for dry eye comfort. The exact same person experiences both, which basically eliminates a whole bunch of confounding variables.
And taking experiments to the absolute maximum scale, we have community intervention trials. This is where an intervention is applied to entire communities all at once. A perfect example is a massive school-based vision screening program, where entire school districts are provided with free glasses to see if it improves overall academic performance. It's basically an extension of a field trial applied broadly to the real world to measure true large-scale public health impact.
Finally, Section 6, choosing the right tool, matching the design to the goal.
So, with all these tools laid out, from single case reports to massive community trials, how does a researcher actually choose the right one? Well, it maps out beautifully. The choice of design entirely depends on the research question. If your goal is to test the efficacy of a brand new medication, you absolutely need the rigorous control of an RCT. If you're trying to understand risk factors and what might be causing a disease over time, cohort and case control studies are your best bet. And if you just need to measure the current burden of a disease to see how bad a problem is right now, cross-sectional studies give you that immediate snapshot. Ultimately, whether it's a humble case report noticing something strange in a single patient or a massive, highly funded randomized trial, every single design has specific strengths and limitations that dictate its use. There really is no one-size-fits-all in epidemiology. It's entirely about matching the right level of investigation to the specific medical mystery at hand.
So I want to leave you with this thought. The very next time a news headline tells you something is definitively bad for your health, or that a miraculous new cure has been found, ask yourself, what kind of medical detectives were on the case? Did they just take a quick snapshot survey, or did they conduct a rigorous, forward-looking randomized trial? Because once you understand the toolkit, it completely changes how you see the science. Thanks for joining me on this explainer, and keep questioning the evidence.